to chemistry with Crip, I guess. So I felt inspired to do this. Thank you to Son, who's the cameraman.
Yes.
I felt like in class we had to cut things short a little bit, so I wanted you to have a full breakdown of how to approach this problem. I was going over Bca tables today, not to make things purposefully obtuse, but to show you that we will need this technique as we continue. To be honest though, there will be an easier way to solve this problem, so I will go over that as well. But let's start with Bca table. So we were given in this problem the chemical equation, and here we have 5 times 10 to the third kilograms of each of NH3, of O2, and of CH4. Of course, you'll have different values on WebAssign. The first thing that I did here was took 5 times 10 to the third and converted that to grams. Of course, kilo means 10 to the third, so 10 to the third times 10 to the third is 10 to the 6th. So 5 times 10 to the 6 grams of NH3. Converting using molar mass, I can find the moles of NH3. And so I can take, again, the grams of O2, converting using molar mass, I can find the moles of O2, and converting using molar mass, I can find the moles of CH4. At this point, this is my B, standing for before the reaction has taken place. So, before, but in order to proceed, we need the limiting reagent. And as I discussed in class, there's kind of 2 ways to do this. One way is through inspection, but inspection only works if it's guaranteed, meaning like you know without a doubt that by inspection that you have the limiting reagent. Honestly, if you were to estimate the limiting reagent another way using a Bca table, you would actually end up with a negative value if you use the incorrect limiting reagent. So actually that is kind of a built-in check for Bca tables. If you do just by conversions, that will not be the case and the answer will just be wrong. So how do I know by inspection? Well, O2 is the smallest value of these 3 and the recipe is requiring O2 the most. So I know I'm guaranteed that just by inspection that oxygen is the limiting reagent. But what if I could not do that? Well, then I would need to take my moles of NH3 and my moles of O2 and my moles of CH4 and really convert them into another substance, one substance to compare. Here I'm converting them to moles of O2, but that's not necessary. I can convert them to moles of NH3 or moles of CH4. What is necessary is to do that conversion and then compare. So I'm converting them using the recipe. So I'm taking my moles of NH3, and there's 2 moles of NH3 that will be required to 3 moles of O2. And so this is the amount of moles of O2 needed to fully react with this NH3, right? Here I'm doing a similar thing with CH4, and here I have the moles of O2 needed to fully react with CH4, right? So you can clearly see that here 4.68 times 10 to the 5th is larger than 4.41 times 10 to the 5th, which is clearly larger than 1.56 times 10 to the 5th moles of O2 that I actually have. So what does this information say? This actually tells us this will run out first, and NH3 would actually run out second, and CH4 would run out third. But it's the limiting reagent that really we need in order to do the calculation. So I'm going to just put at the top, limiting reagent. I'm going to now complete my table here. So the reactants will decrease over time.
There's something on the camera. Oh, there we go. Okay.
There we go. We had some camera issues.
Sorry.
All right. So this will decrease over time because they're reactants, right? If you're using them in the recipe, they will decrease. And whatever you're cooking, whatever you're baking, will increase over time. So minus, 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 plus, plus. And how are they related? By the coefficients. Right? So this will decrease by 2x, and therefore this will decrease by 3x, and this will decrease by 2x, but this will increase by 2x, and this will increase by 6x. You say, what's x? That's the whole point. We're trying to find x. So how can we find x? Using the limiting reagent, because the limiting reagent tells us that afterwards, there will be nothing remaining of that O2. Nothing remaining, 0. So, based upon that, before plus change is equal to after. Before this, moles of O2, minus 3x 3x is equal to 0. I can rearrange, adding 3x to both sides. So 3x is equal to that many moles, right? And then I can divide both sides by 3, and now I have x. That x is the same value as in every one of these changes right there. I have solved for x. Based upon that, I can substitute in for x. Right? Here is after this value minus 2x. And of course, I can just substitute in for x right here. That value minus 2 times that value is equal to that moles of NH3 left over. And I can convert that back into grams if necessary. That's the mass of NH3 left over, not reacted. I can do the same thing with CH4 over here. See? Got our initial value minus 2x, right? And substituting in for x, I can now find the moles of CH4 that was left over. Multiplying by the molar mass, I can find the mass of CH4 left over. I can do the same thing over here. For after the amount of HCN produced, 2x, 2 times x. And then that moles of HCN converting to mass, I can find the grams of HCN produced. Right? And then same thing with 6x, 6 times that x value, I can find the moles of H2O. Converting using grams, I can find the mass of H2O produced. You might say, what is the convenience of this method? It's a little bit of front-loading work, but if you needed to find all of this information all at once, it is very, very convenient. There will be problems in the future where that is absolutely required to do, where you need both pieces of information, both the reactants and the products. Okay, but for us, as we review stoichiometry, you should be familiar with this. There's also another way to do this, perhaps you might say a little bit more convenient. So let's shift over here. So, but really we're doing the same thing, we're just kind of cutting out the table, really. So here, again, I'm starting with our 5 times 10 to the 6 grams of NH3, 5 times 10 to the 6 grams of O2, 5 times 6 to the 10 to the 6 grams of CH4. Converting using molar mass, I can find moles of NH3, moles of O2, moles of CH4. Of course, what I would need to do again is to determine the limiting reagent. Yeah, I already did that in the last problem, but why not? You'd have to still convert. And here in this case, I converted to moles of NH3. See here, moles of NH3 is 3.12 times 10 to the 5th moles of NH3 needed to fully react with the CH4. Here I have 1.04 times 10 to the 5th NH3 needed to react with the moles of O2. And here's my actual moles of NH3 that I have in this problem. Notice carefully, again, this is the smallest value. But it's not NH3 that will run out. This is indicating our limiting reagent, which is O2. This is what will run out. Of course, this is what's projected needed to fully react with this. This is smaller than this and this. Of course, in the same example, you can compare and say, oh, O2 would run out first, NH3 would run out next, and then it's CH4 that would run out third. Because of that, I'm going to now use this value to do my conversions. So here's my moles of O2, and the problem, this specific problem, asked me to solve for grams of HCN and grams of H2O. So really, I'm cutting out the table, but I'm doing exactly the same steps. I'm going to use this value to calculate moles of HCN, and then from moles of HCN, converting using molar mass, I can find my grams of HCN produced. Same thing over here. I can take the mole ratio, again coming from the balanced chemical equation, and then convert using molar mass to find the mass of H2O produced. You need to be familiar with both methods. Now, I know at this point, many of you will probably opt to do this. But you will see increasingly in the course how Bca Table is going to be definitely required. Honestly, when it comes to precipitate problems in which you have equilibrial systems, you're going to see how we're going to combine them. You can't really use this. This actually wouldn't work because, well, we'll get to that. So, again, you want to be familiar with both. The last thing I thought I would do, I think one of the other problems had a percent yield in it. And percent yield is actual over theoretical times 100%. Let's understand what we mean by actual. Actual is reality. It's what is actually produced. Theory is based upon our calculation. Okay? So, In this problem, for me, they gave me given 86.3% yield of copper actually produced. I'm sorry, let me say that again. 86.3% yield of copper produced. That's an important thing. So they are asking me to solve for actual. They are giving me the percent yield. So it's kind of already the ratio of actual to theoretical. What I need to do to solve for actual is to find my theoretical. So they're giving me also 2.5 metric tons. That a metric ton is 10 to the 6 grams. So 2.5 metric ton, 2.5 times 10 to the 6 grams. I can convert that to moles using my molar mass. I can convert that to moles of copper using the mole ratio of the balanced chemical equation. What's that? That's my recipe, right? 2 moles of this plus 7 moles of this will give me 6 moles of that, and 2 moles of that, and 6 moles of that. Of course, I just need the ratio between bornite and copper. So I'm going to now convert, after I'm converted to copper, convert to grams of copper, and that's the theoretical mass of copper that will be produced. I can substitute that in, so 86.3% is what I'm given. Here that's the theoretical. I'm solving for actual. Of course, you can divide both sides by 100%. That's going to be 0.863, and then I can multiply that by the actual mass of copper. No, not the actual, the theoretical mass of copper. And that will give me the actual mass of copper that was produced during this process, 1.47 times 10 to the 6 grams of copper, or 1.47 metric tons. Till next time, crip.